Okay, class, welcome to Physics 203 video class number 16 on expectation values. And here's where we'll start to get experience using the Schrödinger equation to get at real physical quantities like position and momentum and energy, and in general develop our intuition for the rather formidable Schrödinger equation that we learned in the previous lecture. So expectation values are what connect the wave function to physical quantities, as I mentioned, like momentum, energy, and position, and later angular momentum or angle in certain other systems. So what are expectation values? Well, whenever we take measurements, we have an expected, we can say we have an expected value of a measurement in physics and elsewhere. So for example, if we have a graph of the average rain per month in Boston, Massachusetts, we can say that we have a, it varies from month to month, but on average, we can say there's an expected value somewhere in between, and we know how you would know how to take the average of that set of bars if you knew the individual values. Likewise, with heights, we're not all the same height, so there's variation in heights, but we can say there's an expected value of a height. The average male in the United States, I believe, is about 5'10", and the average female around 5'6" or 5'7". So I guess that puts the average person at around 5'8" or 5'9". Or stock prices, if you're into finance or you like to play the stock market, stock prices fluctuate from day to day and month to month. In this case, I guess this would be month to month. But we can take an average over intervals of time. So then average over this interval of time would be less than an average over this interval, and so forth. So we have this notion of an expected or average value of a measurement. As I said, quantitative measurements vary from instance to instance, and we characterize them by both an expected value, an average value, which is indicated by this red bar here for these 5 individuals here about their average or expected height, and also a variation, how far they range around the average value. Do they range from tiny little dwarves to huge giants, or do they range more tightly in just a range of a few inches? And in this case, we know that it's just a few inches, that most of us are within a foot of, let's say, of the same height. So we'll be focusing mainly on the expected or average value in our studies of quantum physics here, but just know that the variation is, which is also known in some cases as the fluctuation or the standard deviation, if you've taken statistics, actually plays a key role in quantum physics as well, and in other branches of physics, like especially thermal and statistical physics. But okay, let's move on to expected or average value. So how would we define that? Well, let's start off with a discrete distribution. So here's a discrete distribution of numbers where we have number x1, which occurs n1 times, number x2, which occurs n2 times, number x3, which occurs n3 times, number x4, which occurs n4 times, and so forth. And the expected value would be just the weighted sum of the individual values, x1, x2, x3, x4, times the number of instances that each one occurs over the total number of instances. And in summation form, that would be the sum over all possible values of each value times the number of times that value occurs divided by the total number of values. So if that seems a little abstract, let's take an example here. Let's say we have 3 possible values. We have values x1 equal 1, x2 equal 2, and x3 equal 3. So three values here. And we have 2 instances of x1 equal 1. We have 3 instances of x2 equal 2, represented by these 3 balls here. And we have 1 instance of x3 equal 3. Okay? So what would be the expected value of x in this case? Well, using this formula over here, we would say the expected value of x would be n1, which is 2, since there's 2 of these, times that particular value, plus n2, since there's 3 of those, times that value of 2, plus n3, there's 1 of the third value, times that particular value, which is 3, over the total number of values, which would be, in this case, 2 plus 3 plus 1. So that'd be 2 plus 6 plus 3, or 11 over 2 plus 3 plus 1 is 6, 11, 6, or 1.83. Okay? So that's how we would find the expected value for a discrete set of measurements. In terms of continuous, we generalize it by replacing, as we do in calculus, a sum, like this sum here and this sum here, by an integral. Instead of summing up all of the different instances ni, we integrate over all possible values, here taken to be minus infinity to infinity, the probability. Remember, the probability is the probability density p of x times dx. And in the so the px dx terms are like a series, n1, n2, n3. And in the top integral, each of these px dx values are weighted by their individual x values, just like in the discrete sum, each each of the numbers here, n1, n2, and n3, are weighted by the particular value that they represent. Okay, so this would be the general formula for continuous. Now, specializing to quantum physics, we can get a handle on the position expectation value, okay, the expectation value of position, using the quantum probability density. So the quantum probability density, you remember, is psi star times psi. So the probability density is psi star times psi. The probability would be the probability density times dx. So this represents a probability, and just psi star psi is the probability density. So just substituting in for p of x as our probability density, we get this formula for the expectation value of x, which is indicated by these brackets. These brackets indicate an expectation or an average value taken over many possible measurements over the probability distribution. So it would be x psi star psi integral over psi star psi. And notice that this bottom form here is the integral of the probability density over all space, which, if the wave function is normalized, would be 1. So if we're dealing with a normalized wave function, this denominator would automatically be 1. And then finally, and this is one of the shorter lectures in the recent series, You might wonder how we can get the momentum expectation value. How can we get at a quantity like momentum when the wave function seems to key so strongly on position? So we use what's called an operator. So let me explain. So can we measure? We can measure position. How can we get at quantities like momentum or energy? Okay, so consider the complex plane wave solution, which we dealt with last time, which solves the time-dependent Schrodinger equation. This amplitude A times e to the I kx minus omega t. All right, so this is like a traveling complex wave. Just think of it like a wave traveling through space. If we take a partial derivative, which you know how to do now with respect to x, that all that does is bring down, as you've read and attempted, that just brings down an ik. So the partial derivative of psi with respect to x is the partial derivative with respect to x of, let's see, it looks like we're missing an a here. But in any case, that would be equal to just ik, since we ignore the t part, since the partial is with respect to x, ik times e to the ikx minus omega t. And e to the ikx minus omega t is psi, okay? So we just get the partial derivative of psi with respect to x is ik times psi back again. But that's interesting because k, we know the wave number k is related to the momentum. P is equal to h bar k, so k would be p over h bar in quantum physics. That's a form of the de Broglie relationship. And so this d psi dx equals I k psi can be written as k can be substituted as p over h bar psi. Okay, so I'll pause to let you sort of digest that for a second. Or if we rearrange this, then bringing up h here and dividing by I, and recognizing that 1 over I is actually equal to minus I. You can check that if you want. But 1 over I is equal to minus I. We get the right-hand side becomes then P times psi. So P times psi is equal to bringing up the h bar minus I h bar d psi dx. Okay? So it looks like this operation of taking minus I times h bar and the derivative with respect to x sort of extracts the momentum p out of the wave function. It gives us the wave function times the momentum p of it back again. So we can look at this operation of taking minus I h bar d psi dx, or so-called operator minus I h bar d dx. It's called an operator because it's waiting to operate on something. It's a derivative. It's waiting for a function to do something to, as being associated with, or really extracting the momentum from psi, as in this case. So if we take minus I h bar d psi dx, we get the momentum times the wave function back again. So the expectation value of momentum is then equal to Q, which is just a general letter used to represent these operators, which would be equal to the psi star times Q hat times psi dx, where the operator Q hat is minus I h bar d dx. Okay. So then we kind of have this cute notation, I should say, or we can write this as more specifically, since we're dealing with momentum, as P equals bringing out the minus I h bar, bringing out the minus I h bar, just psi star, and then the derivative with respect to x of psi. Okay, so this would be a more explicit formula. But as to the operators Q, we distinguish them from ordinary numbers with a hat. Okay, so Q hat, or P hat, or X hat, or E hat, just means it's an operator. That is, it's not a function. It's something which acts on a function to produce another function. So it wears this caret, which I've represented as this little top hat here. And in the expectation value formula for P, let's say, or for a general operator Q, the operator Q with its hat is like, I like to think of it like the middle of a sandwich between psi star and psi. So psi star is your nice top piece of bread. Q hat is your juicy piece of salami and cheese, and psi is your bottom piece of bread here. Okay, so and then you integrate it all together and you get a whole sandwich and you just eat it right up. Okay, so it's like an operator sandwich. Psi star times your operator times psi. That's pretty much what I wanted to communicate to you. And similar arguments, if you see section 6.2, using, instead of the relationship for K and P and H bar, or P is H bar K, using E as H bar omega, establish that the energy operator turns out to be, instead of minus I H bar ddx, I H bar ddt. Okay, so it's not surprising it's related to the time, because energy is related to frequency, while momentum is related to wave number, which is related to space, or x. And the expectation value for E would be I H bar psi star d psi dt dx. Okay, so what have we learned? We've learned that things vary, measurements vary, and we can characterize them by an expected or average value, as well as a variation. We're concentrated on the expected value. We learned how to take a discrete, an expectation value for a discrete set of data, and we also learned how to do it for a continuous distribution. And then we specialized to quantum physics, which has the probability density for the discrete distribution given by psi star psi, to figure out how to get the position expectation value. And then we used these de Broglie relationship and the Planck relationship to figure out how to extract expectation values, that is physical quantities, for the momentum out of the wave function. Okay, so this may still seem a bit abstract, but we'll get some practice in working problems on this, and you'll see how this strange complex object of the wave function gives us these actual physical quantities like momentum and energy of a particle. So I appreciate your attention and look forward to seeing you in class.